Alright, here I'm going to go over a Hardy-Weinberg practice problem. This will hopefully clear up any issues you might be having and help give you an example and work it through so you can understand the process that you go through. Remember, don't practice until you get it right, practice until you can't get it wrong. So review this as many times as you need to, and hopefully this will be overall helpful with you understanding the process. So, Hardy-Weinberg problem. Down here, remember, this is our equation we'll constantly be dealing with. This will be constant. You're welcome to use your calculator to help yourself work through this problem. So given a population of 100 individuals, remember diploid individuals, so 200 total alleles, 16 exhibit a recessive trait. So the problem is to find the allele frequencies for big A and little a, and find the genotype frequencies for the homozygous dominant, the heterozygous, and the homozygous recessive. This is all you would be given, and you'd be expected to find these answers. In this video, I'm going to go through this stepwise process to help you gain some experience. So the allele frequencies we want to calculate first. How are we going to go about doing that? Well, P plus Q equals 1, and since P equals a big A and Q equals little a, then we can simply say big A plus little a will equal 1. So the question is, something out of 200 plus 32 out of 200 will equal 200 out of 200. You need to work with the total alleles. So where did the number 200 come from? That was the total alleles. Where did the 32 come from? Well, the 16 that exhibit the recessive trait mean that they're these individuals here. They're the homozygous recessive. So 16 times 2 is the 32. So if this equals the 16%, then something plus 16% has to equal 100%, which means 84%, because 84 plus 16 is 100, 84% are a combination of the homozygous dominant and the heterozygotes. Now, in order to calculate what the homozygous dominant and the heterozygotes are, we need to take this the next step further. So 16% in decimal form is represented by 0.16, and this is the same as q squared, because our two little a's are q and q, or q squared, represented right here. Remember, that's our recessive, or 0.16. We simply take the square root of that to get q, which is 0.4. Now, if this one's 0.4, we know 1 minus q equals p, or 1 minus 0.4 is 0.6. So the dominant allele here is represented by 0.6, and the recessive allele by 0.4. This is a big help because now we can start to input this into our equation and help answer the genotypic frequencies. So the phenotype frequencies, if p equals 0.6 and q is 0.4, then we simply plug into the equation. P squared is 0.6 times 0.6, which is your 0.36. Q squared is 0.4 times 0.4, which is 0.16. And the heterozygotes, 2pq, 2 times 0.6 times 0.48. What these decimals refer to is the homozygous dominant represent 36% of the population. The heterozygous dominant is 48%. And the recessive is 16%. Hopefully this is helpful, and I'll go through an example here to help you understand how to calculate the Hardy-Weinberg equation. And to test your knowledge, here is another question here. Fraggles are mythical mouse-like creatures that live beneath flower gardens. If 100 fraggles in a population, of the 100 fraggles in a population, 91 have green hair. We're going to represent with capital F, and 9 have gray hair, lowercase f. Assuming genetic equilibrium, what are the gene frequencies of big F and little f, and what are the genotypic frequencies? I invite you to pause the video here so you can go through and work this problem on your own before I proceed with the answers. Alright, we're going to proceed now with the answers. Hopefully you can compare your own to the answers that I have presented here. So the answers are simple. F is 0.7, little f is 0.3, and going through our Hardy-Weinberg equation, as you can find at the beginning of this video, the homozygous dominant is 49%, the heterozygous is 42%, and the homozygous recessive is 9%. This is another graphical representation to help you work through the problem, and kind of shows it with the Punnett square if that helps you understand it a little bit better. But I invite you to go back and review this video so you can feel comfortable calculating with the Hardy-Weinberg equation.